Welcome to the Things of the Stars, Sleeping with Science series. These journeys invite you to slow down, quiet your thoughts, and drift into rest while exploring the wonders of the universe. If you enjoy these moments of calm discovery, support us by subscribing to this channel and visiting thingsofthestars.com. In this episode, we are turning our gaze outward, contemplating the universe that surrounds us and the mysterious shadows that govern it. We are going to explore the invisible scaffolding that holds the stars in place, a presence that defies our senses, yet defines reality itself. Consider the ordinary matter that makes up your body, the bed beneath you, the air you breathe, the planets, and all the glittering stars visible in the night sky. Everything we can see, touch, or measure directly with light constitutes only a tiny fraction of existence. Everything we know is just 5% of the universe. The rest, the overwhelming majority, is something entirely unseen. Take a breath. The universe is patient. In the late 19th century, long before modern cosmology, there were early, quiet musings about this hidden mass. Lord Kelvin, speaking in 1884, speculated that many stars around the sun might be dark bodies, contributing mass without contributing light. These were small, hesitant whispers about unseen mass. The whispers grew louder in the early 1930s. A Dutch radio astronomy pioneer, Jan Oort, hypothesized the existence of dark matter in 1932 after studying stellar motions in the neighborhood of the Milky Way, finding that the mass in the galactic plane appeared greater than what was visible. Then came the startling insights of Fritz Zwicky, a Swiss astrophysicist who studied the movements within the Coma Galaxy cluster in 1933. Zwicky noticed that the galaxies in the cluster were moving so quickly that the cluster should have simply flown apart. It needed enormous, unseen gravitational glue to hold it together. He estimated that the cluster contained perhaps 400 times more mass than he could observe in luminous stars. He called this phenomenon Dunkel Materie, German for dark matter. Though Zwicky's initial numbers were off by an order of magnitude due to outdated constants, his conclusion was correct. Most of the gravitational matter present was dark. This was the initial, bold pronouncement of the missing mass problem. For decades, many scientists assumed this missing mass might just be ordinary matter that was too dim to see. Things like dead stars, brown dwarfs, or gas clouds, collectively known as massive compact halo objects, or MACOs. But modern evidence, gathered from the vastness of space, points towards something far stranger, a non-baryonic component, meaning it is not made of the protons and neutrons that form atoms. It is a substance in the universe that has mass, but does not give off or reflect light, making it invisible to the entire electromagnetic spectrum. Dark matter, this invisible and hypothetical form of matter, makes up about 85% of the total mass of the universe. It accounts for roughly 27% of the universe's total mass and energy content. It is a profound mystery, an unseen influence that shaped everything you see tonight, and yet we know more about what it is not than what it actually is. Drift into that quiet sense of wonder. The greatest part of reality is a secret, waiting to be found. Our surest evidence for dark matter comes from observing its effects, specifically its gravitational influence. If we cannot see it, we must observe how it tugs on what we can see. The mystery truly took hold in the 1970s. Imagine a spiral galaxy, like a magnificent, slow-turning pinwheel of stars. Stars orbit the center of the galaxy, much like planets orbit the sun. Based on the visible light, most of the mass should be concentrated near the center. Therefore, Newtonian laws of gravity predicted that the stars farther out should orbit more slowly, just as the outer planets in our solar system are sluggish compared to the inner ones. This is known as a Keplerian orbit profile. However, when astronomers measured the rotation speeds of spiral galaxies, they found something astonishing. The American astronomer Vera Rubin, working alongside Kent Ford, used a new spectrograph to measure the velocity curves of edge-on spiral galaxies with impressive accuracy. Her detailed optical data, confirmed in parallel by radio astronomers mapping atomic hydrogen gas, which extends far beyond the visible edge of the galaxies, revealed a massive inconsistency. The outer stars were orbiting just as fast as the stars near the center, creating what scientists call flat galaxy rotation curves. For instance, measurements of the Andromeda Galaxy showed that rotational velocity remained constant even far beyond the visible light's edge. The visible mass simply wasn't enough to provide the gravitational pull needed to keep those outer stars moving so quickly. Otherwise, they would fly off into space. This required a huge amount of missing mass, distributed not just in the visible disk, but in an expansive sphere or cocoon surrounding the galaxy. This structure became known as the dark matter halo. It was realized in the 1970s that every galaxy likely sits within a vast, invisible cocoon, several times more massive than the visible stars and gas combined. Think of a gentle, invisible hand holding the outermost edge of a spinning carousel, preventing the horses from flying into the night. That is the dark matter halo, revealed only by the motions it commands. This rotational anomaly became the foundational evidence for dark matter, forcing astronomers to alter their preconceptions about the makeup of the cosmos. Take a breath. Allow your shoulders to relax, heavy with the pull of gravity, a force we understand, yet one that carries the signature of the invisible. The evidence for dark matter only strengthens when we look beyond individual galaxies, scaling up to the grandest structures in the universe, galaxy clusters, and the cosmic web itself. Galaxy clusters, building on Zwicky's original work, provide multiple, independent ways to measure mass. Scientists can calculate mass based on the spread of galaxy velocities within the cluster, or by measuring the X-rays emitted by the vast clouds of hot gas trapped inside. Critically, the gravity from these visible components, the galaxies and the hot gas, is still insufficient to bind the cluster. These three methods generally agree, confirming that dark matter outweighs visible matter by about 5-to-1 in these massive structures. The most striking visual confirmation comes from observing cosmic collisions. Imagine two massive galaxy clusters slamming through each other. This event created the bullet cluster. Astronomers studied this cluster and found that the hot, ordinary gas in the clusters collided, slowed down, and glowed in X-rays, appearing as pink clouds in the image. However, when scientists mapped the actual mass distribution using a technique called gravitational lensing, they found that most of the mass was located elsewhere, in two separate blue clumps. Gravitational lensing is one of the consequences of general relativity, where massive objects bend the path of light traveling from a background source. By measuring how the gravity of a cluster subtly warps the shapes of distant background galaxies, scientists can determine where the mass truly resides. In the bullet cluster, the invisible mass, the dark matter, simply passed right through the collision without slowing down or interacting. It separated cleanly from the visible gas. This separation acts as a direct empirical proof of the existence of dark matter, showing that most of the cluster's mass is a non-interacting, collisionless substance. The same principle of gravitational bending, applied in a subtle way, helps us map the largest structures in the cosmos. This is called weak gravitational lensing, where the light from distant galaxies is only minutely distorted as it passes through the vast filaments of mass connecting superclusters. This collective distortion must be calculated using billions of galaxies to reveal the underlying dark matter distribution. Now, lift your mental eye to the entire universe, just 380,000 years after the Big Bang, a time before stars or galaxies even existed. Satellites like WMAP and Planck have mapped the cosmic microwave background, or CMB, which is the faint afterglow of this early hot universe. The CMB is almost perfectly uniform, but it contains tiny temperature fluctuations, small anisotropies, only a few parts in 100,000. The pattern of acoustic peaks in the CMB data provides powerful constraints on what the universe is made of. To match these peaks with theory, the universe must be mostly dark. Specifically, these measurements reveal that roughly 26% of the total energy density is dark matter, fitting neatly into the standard lambda. Dark matter is thus not only necessary to keep galaxies and clusters intact, but it was also essential for forming the structure of the universe itself. Dark matter clumped first under gravity, forming gravitational scaffolding, or a cosmic web, which then provided the potential wells for ordinary matter to collapse into, eventually forming galaxies and clusters. If there were only ordinary matter, there would not have been enough time for density fluctuations to grow into the complex structures we observe today. Let your mind rest within the cosmic web, that invisible framework that underlies all visible beauty. If dark matter is real, then what is it? The prevailing opinion among cosmologists is that dark matter consists primarily of some type of yet-to-be-characterized subatomic particle. This particle would interact with ordinary matter only through gravity, and perhaps through forces as weak as or weaker than the weak nuclear force. Based on its speed, dark matter can be classified as hot, warm, or cold. Hot dark matter, like known neutrinos, moves fast and tends to smear out density fluctuations, preventing small structures like galaxies from forming first. Cold dark matter, or CDM, moves much slower, and models based on it suggest that smaller structures, galaxies, formed first, followed by larger clusters. Because deep field observations show that galaxies did form first, the favored scenario is cold dark matter. For decades, the leading candidate for the dark matter particle was the WIMP, the weakly interacting massive particle. The WIMP hypothesis gained immense traction in the late 1970s because theorists realized that a particle with a mass in the range of 100 GeV, roughly a heavy atom, and interaction strength similar to the weak nuclear force, would naturally freeze out. This apparent perfect fit is famously known as the WIMP miracle. Furthermore, extensions to the standard model of particle physics, like supersymmetry, readily predict stable particles, such as the neutralino, which fit the WIMP profile. The search for WIMPs is one of the major efforts in particle physics. Since we cannot see them, we have to try to catch them in the act of interacting. One main strategy is direct detection, where scientists search for the extremely rare event of a dark matter particle scattering off an atomic nucleus within a highly sensitive detector. Because interference from cosmic rays must be minimized, these experiments are located deep underground. Imagine waiting for a ghost to bump a feather. Current world-leading detectors include the Xenon and T experiment in Italy and the LZ Lux Zeppelin experiment located deep beneath the Black Hills of South Dakota. These experiments utilize large tanks of ultra-pure liquid xenon kept at extremely cold temperatures. If a WIMP interacts, it gives a tiny recoil kick to a xenon nucleus, producing a faint flash of light and ionization electrons that produce a second light signal. These experiments are designed to distinguish these tiny WIMP-like signals from background noise, such as gamma rays or neutrons. Both XEN-on-T and LZ have demonstrated incredible sensitivity, setting stringent new limits on how often WIMPs can interact. For example, results from the LZ collaboration in 2024 found no evidence of WIMPs above a mass of 9 gigaelectron volts. Likewise reported data consistent with the background-only hypothesis, meaning no clear WIMP signal was detected. These null results do not mean dark matter is absent, but they narrow the possibilities, forcing theorists to explore particles that interact even more weakly or perhaps have a different mass range. The detectors are now becoming so sensitive that they are approaching the neutrino floor, where signals from neutrinos, the most elusive known particles, start to obscure the potential dark matter signals. Given the non-detection of WIMPs, physicists are also focusing intensely on alternatives. One well-motivated candidate is the axion, a very lightweight hypothetical elementary particle originally theorized to solve a problem in nuclear physics known as the strong CP problem. Axions could also account for some or all of the dark matter and are considered by many to be a natural and elegant solution. Experiments like the Axion Dark Matter E-experiment, or ADMX, are designed to search for these elusive particles. The hunt also extends to the Large Hadron Collider, or LHC, where physicists attempt to produce dark matter particles directly. Since dark matter should have negligible interactions with visible matter, a successful production event would be detected indirectly as a large amount of missing energy and momentum that escapes the sensors. So far, the LHC has not confirmed any new stable particles fitting the dark matter profile. Feel the weight of the unknown. That substance, passing through you billions of times every second, undetected. The extraordinary reliance on an invisible entity naturally leads to a profound question, a question scientists and philosophers constantly ask. If we see inconsistencies in cosmic behavior, are we missing mass or are we missing physics? This is a classic example of what philosophers call the underdetermination of scientific theory by the available evidence. The strange rotation of galaxies could be solved either by adding unobservable matter or by declaring that our gravitational laws are incomplete. The most prominent alternative to dark matter is modified Newtonian dynamics, or MUND. Introduced in 1983, Mund suggests that Newton's law of gravity may work differently at the extremely low accelerations found at the outskirts of galaxies. By tweaking the way gravity behaves on these vast scales, Mund successfully reproduces the flat galaxy rotation curves without needing any extra mass. Mund's success in describing galaxy dynamics is impressive, indicating that it captures something important about how gravity works on these scales. However, the scientific community overwhelmingly favors the dark matter hypothesis, incorporated into the standard cosmological model called lambda cold dark matter, or YCDM. Why this strong preference if Mund can explain galactic rotation? The answer lies in the breadth of evidence. The dark matter hypothesis offers a unified explanation for wildly different phenomena across all scales of the universe. While Mund can be tuned perfectly for galaxy rotation curves, early versions struggled to explain the observations of galaxy clusters and, crucially, the cosmic microwave background. To match these cosmological observations, modified gravity theories often need additional tweaks or new fields, which begins to complicate the model. The SCDM model, using a single assumption, the existence of cold, invisible matter, elegantly accounts for the rotation of galaxies, the mass distribution in galaxy clusters, like the separation seen in the Bullet cluster, the pattern of peaks in the CMB, and the formation of the large-scale cosmic web. This coherence and comprehensive explanatory power make the dark matter model the preferred choice, an example of inference to the best explanation. Nonetheless, research continues into alternative forms of dark matter too, which are rooted in well-understood physics. One intriguing possibility is that dark matter consists of primordial black holes. These are hypothetical black holes that may have formed in the chaotic, high-density period just after the Big Bang. Because their formation predates the first stars, they are not classified as baryonic matter, and since they are known objects obeying general relativity, they have a major theoretical advantage. The detection of gravitational waves from merging intermediate mass black holes in 2015 briefly gave this idea prominence, as these objects were not easily explained by standard stellar collapse. While certain mass ranges have been ruled out by observing gravitational microlensing, there remains an unconstrained window where primordial black holes might still account for all dark matter. Relax your muscles, softening into the comfort of your bed. The debate between hidden mass and modified physics is a healthy one, driving us deeper into the truth. The quest to characterize dark matter defines the next era of cosmological research. The coming years promise to bring data with unprecedented precision, thanks to a new generation of sky surveys and detector technologies. In space, the European Space Agency's Euclid mission is specifically designed to probe the dark universe. Launched in 2023, Euclid is tasked with creating a massive 3D map of the universe, covering more than a third of the sky and reaching back 10 billion years in cosmic history. Euclid will use the technique of weak gravitational lensing to map the distribution of dark matter scaffolding with high fidelity, showing how it evolved as the universe expanded. This map will test whether dark matter behaves exactly as the cold dark matter simulations predict, or if small deviations hint at new properties, such as self-interactions. On the ground, the Vera C. Rubin Observatory, named in honor of the pioneering astronomer Vera Rubin, is set to begin its Legacy Survey of Space and Time, or LSST, in the mid-2020s. The observatory utilizes an 8.4-meter telescope equipped with the largest digital camera in the world. This massive data collection, involving billions of galaxies, will give scientists the statistical power needed to map dark matter using weak lensing with exquisite precision. By charting the distribution of dark matter and studying how it competes with dark energy, dark matter attempting to build structures, dark energy attempting to push them apart, Rubin will place firm constraints on the equations describing the universe. This influx of high-quality data will test the lambda CDM model more stringently than ever before. If Rubin or Euclid revealed discrepancies, such as finding fewer dwarf galaxies than expected or unusual density profiles, it could point towards dark matter having slight self-interactions, suggesting it is warm or self-interacting dark matter. Meanwhile, particle physicists are pushing the sensitivity limits of their instruments. Future direct detection projects, such as the proposed Darwin Observatory, aim to increase sensitivity even further, trying to probe WIMP interaction rates predicted by advanced theories. Indirect searches, such as the upcoming Cherenkov Telescope Array, or CTA, will enhance the search for gamma rays resulting from dark matter annihilation. The ultimate hope is for convergence. Imagine a scenario where a pattern detected by the Rubin Observatory suggests a specific dark matter property, and then a dedicated lab experiment finally catches the particle with those exact characteristics. The challenge of dark matter has pushed us to imagine entirely new realms of physics, from graviton clumps, microscopic objects made of the quantum particles of gravity, to particles tied to extra dimensions. Whether we ultimately find a particle, or whether we find that gravity itself needs fundamental revision, dark matter remains a powerful driver of knowledge. Now, as the stillness of the night deepens, we conclude our journey into the mystery of dark matter. It is a humbling thought. 95% of the cosmos, dark matter, and the accelerating force of dark energy remains invisible to us. The ordinary matter that forms our world is merely a luminous frosting on a colossal dark structure. Dark matter is defined by its gravitational pull. We infer its existence not from seeing it, but from observing the effects of its immense weight on everything that shines. It is like standing in a deep valley, sensing the surrounding mountains even if they are cloaked in fog. The story of dark matter is a detective story still being written. It teaches us that science progresses best when observations force us to alter our deepest preconceptions. It reminds us that our perception is limited and that fundamental reality extends far beyond the light we rely on. Rest now, knowing that you are surrounded by the unseen complexity of the universe, and that even the empty space around you is teeming with possibility. Allow your breathing to become rhythmic and slow, matching the quiet, patient expansion of the cosmos. Close your eyes, feel the gentle, ancient pull of gravity, and drift toward sleep. The universe is vast, and you are safe within its structures.